Another example here, we got a ladder of length L and mass M leaning against the wall, making an angle theta to the ground. So you get ground, wall, ladder, theta. What forces are acting on this ladder? Well, we have the gravitational force on the ladder. The ground will exert an upward normal force on the ladder. The wall will exert an outward normal force on the ladder. Now, if there was no friction, this ladder would slide down, which means that the frictional forces will resist that. This would tend to go down, so there is friction from the wall going up, and this would tend to slide out, so there's friction from the ground going in. So there are 5 forces going on here. Yeah. And for net torque, you can do whatever you want, but I would set my axis at a point where there are more forces. Depending on what you're given, that might work differently, but if I set my axis of rotation here, then I've got mg, and if the length of the ladder is L, that's acting halfway along. And this is making an angle. The angle it makes the ladder is the complement of this angle, so that's torque is Fr sine theta, so it's sine of 90 minus theta, which is actually the same thing as cosine theta, so you could substitute in cosine theta for that. And that's acting in the clockwise direction, which would be into the page, so negative. Then we've got normal wall acting distance L from the pivot, alternate interior. This angle is theta, so that's then L sine theta, and that will be acting out of the page. And then also out of the page, you have friction from the wall acting a distance L away. This angle right here, what would that be? That's theta, that's 90. Then this angle plus this has to be 90 minus theta again. So that is also sine of 90 minus theta, which is the same thing as cosine theta. Yeah, and for net force, you just have upward, well, net force in the x direction. You have normal ground plus friction wall minus mg equals 0. If it's staying at rest, I guess. It doesn't say it's at rest. And then in the y direction, I'm sorry, that is the y direction. What's my brain doing? And then in the x direction, you just have friction ground minus normal wall. So those are all the forces going on if you have a ladder. Carrying on, example after example. A sine of length L and mass M is hung at, so that one end is attached to a wall, the other end is supported by a cable. So wall, here's a sine. And one end's attached to a wall, the other end is supported by a cable, so we've got a cable attached there, angle of 30 degrees. Sine's center of mass is located at a distance 3L over 4 from the wall. So this tells us that the gravitational force on the sine acts over here. Yeah, and we want to find the tension in the cable, the next net force exerted on the sine by the wall. Well, we don't know how this sine is attached, but we do know that this tension has a leftward component, so there must be the next component of force from the wall to cancel that out. And it will also be true, there could in principle be a y component of the force from the wall, and we'll assume it's upward, and it will be upward. But yeah, but you wouldn't necessarily know that, but if we assume it's upward, we'll calculate and figure it out. Yeah. So we have two unknown components here. So again, makes sense to me to put the axis of rotation over there, because then you eliminate those two from the torque equation. So then in the torque equation, you have tension times, and that's acting a distance L away, times sine of 30 degrees. That's acting in the out of the page direction. In the other direction, you have mg times 3L over 4, acting perpendicular. So that's that. Sine of 30 we know is 1/2. And you can see L goes bye-bye, so we get the tension. The 2 will cancel, so it's 3 over 2. mg is the tension in the cable. In the x direction, we have friction from the wall in one direction and tension cosine 30 in the other direction. So friction from the wall is equal to tension cosine 30, which is 3/2 mg times root 3 over 2. So the x component of friction from the wall, or force from the wall, not friction, is 3 root 3 over 4 mg. And in the y direction, we have a component of tension and force from the wall, y component, and gravity. So force from the wall, y component, equals mg minus t sine 30, which is 3/2 mg times 1/2. Therefore, y component of friction from the wall. Sorry, I just realized that I put a y there, and it should have been x. What is that? 3/2 times 1/2 is 1/4, 3/4, so mg 1 minus 3/4 is 1/4. So you've got the two components, and then we can find the magnitude. So 3 root 3 over 4 is the x component, the coefficient of the x component anyway. And 0.25 is the y component, so square root of x squared plus y squared. That's ugly. If I square it. Aha! So the magnitude is square root of 7 over 2. mg is the magnitude, and then inverse tangent y over x gives us the angle at 10.89 degrees above the horizontal. So that is that one. Moving along. Diver. So this is the diving board problem from before, but with a diver added. So one's at the left end, one's 2.2 meters. Excuse me, we're saying the diving board has negligible mass, but there's a person over here. So again, normal 1, normal 2, mass of the person times g. We set the axis of rotation here. Then for torque, we have normal 2 times the distance, which is 2.2 meters away, minus the mass of the person times g times the distance, which is 9.7 meters. And then we can solve. See that normal 2 is 2938 newtons up. And then from force in the y direction, we have our two support forces, and then mass of person times g. So normal 1 plus 2938 minus 68 times 9.8 equals 0. So calculating, we see that the force from the other pillar is about 2272 newtons down. For B, it's very similar, except now the diving board has mass. And then, so we can calculate the torque equation becomes N2 times 2.2 minus torque from the person. Then we also have torque from the diving board. Its mass is 18 kilograms, G is 9.8, and its distance is halfway down, so 9.7 over 2, which is what, 4.85. So we can calculate that. And we get, in that case, it's about 33.27 newtons upward. And the force equation, we would just add another term for the mass of the board and plug in that value for N2. So we take that minus 68 times 9.8 minus 18 times 9.8. Oops, shoot, I said 8.8. Yeah, so it's that, and it moves to the other side, so it's 2484 newtons. Downward. Problem 7 is fairly complicated. So, supported by two chains that make an angle of 48 degrees above the horizontal. So we've got chain, shelf, and where's the chain attach? Anchored to the shelf. I didn't say, but let's say the chain is at the end, I guess. This is 48 degrees. So we've got some kind of, I don't know, it's not really tension, but we can call it tension. We've got force from the wall X component, force from the wall Y component. We have mass of the shelf times G, and we'll say the shelf is uniform. And there are two objects on the shelf. One is 0.56 meters from the wall, which is ever so slightly more than half of this, so we've got one right here. The other is very close to the wall, M2G. So this is our diagram. There's lots of forces going on. Yeah. So again, for torque, these two unknowns at the wall make it reasonable to put our axis of rotation right there. In which case, we have a torque from the chains that acts, the full length away, and at an angle. And then in the opposite direction, all of them have G attached to them. And then we have a mass of 1.3 kilograms that acts halfway down, so that's 0.505. And then we have a mass of 2.04 kilograms, it's 0.56 meters away. And then a mass of 4.21 kilograms, that's 0.11 meters away, close parentheses, equals 0. And there are two chains that are doing this, so we can just throw in a factor of 2 there. The tension in each chain. We can calculate 9.8 parentheses 1.3 times 505 plus. Calculating, we get the tension is 14.77 newtons. And